bases that dealt with protons being accepted or donated. So my equation here has HCl, which is a strong acid reacting with water, and the H is transferred from the HCl to just the water, making the H3O. Now, specifically, it is the H. So technically what we're seeing here is this bond here that's between the hydrogen and chlorine breaking, but breaking in such a way that the chlorine keeps all of the electrons and the H is the only thing that moves. And technically, on our water, the species acting like the base here, the H just moves to that, and that lone pair becomes a new bond. Now, that's going to happen on any acid and base. We're going to see that the H, or the acid, moves to a spot where the lone pair is. When we talked in Chem 1 and Chem 2, we could distinguish our strong acids and strong bases based on how much the reaction was likely to go backwards and forwards. Most of the acid-base reactions are actually reversible because those are all of our weak acids. That makes up the large majority of them. And all the ones we're going to be mostly focusing on in organic chemistry are reversible. They're the weak acid style. But there are some strong acid reactions we use, but most of the time it's going backwards. Now, how can we tell a difference? It really depends on the species we're working with. HCl, for instance, is a strong acid, has a very small, or has a very large Ka, which actually is the number we use to talk about the strength of an acid. But when it goes forward, when HCl does react, it creates a conjugate base. Conjugate base is the species left over without the H. So HCl, being their acid, gives up the H. Everything left over is the conjugate base. Now, in this case, water is behaving as a base, and that base accepts the proton and becomes the conjugate acid. So acid loses a proton and becomes a conjugate base. Base gains proton, turns into a conjugate acid. All right, that happened anytime, whether we had a strong acid or a weak acid. The only thing that really ever changed on this is our arrows. Now, in Chem 1, we would actually have almost always shown this first one as a one-way arrow only, and that's because HCl is a really, really strong acid, has a very large Ka, very much favors going forward. And something like acetic acid, a weak acid, would have actually had that nice two-way arrow because when it's all done, we still have quite a bit of acetic acid still with the H intact, and very little bit, a very small amount, had the H donated, making the H3O. Now, when we ranked the strengths of a weak acid, and it worked on strong acids, we actually, back in Chem 1 and Chem 2, talked about Kas. And we could actually get tabulated values and look them up. And the Ka was somewhat related to the strength of the acid, as long as you had all the ratios worked out. Now, in organic, we're not going to do any of this with actual math. So there's no math involved when we do this. It's going to be very simplified math when we do any math. So we're not really looking at that. So we just want to talk about values right now. And in Chem 1 and Chem 2, we talked about strong acids and weak acids. And when we got to Chem 2, we finally put the Kas in place. And our very strong acids were pKa's that were less than 1. And all of our rest that we talked about, weak acid-wise, was anything from pKa of 1 to maybe as high as 15. We didn't go out above that because really above that, those are things that aren't really acids at all. They might have acidic-like properties, but they basically don't go forward enough to make it worthwhile to call acids. But that was our range. We had that 1 to 15, and that was our entire weak acid range. All right, we're going to expand on that some as we get into here. All right, now, another thing we're going to talk about or remind ourselves of that is there is a pH scale, and we got a bunch of these things over here dealing with it. Now, a lot of the times we use this maybe not with actual pH values, but we talk about making things more acidic or making things more basic. And that's mainly because we look here, all these possible things that have various different pHs, we got quite a few that would count as organic molecules. So organic molecules can exist at a lot of these pHs without too much problem. and all the rest are easily obtained. And if I needed to change the pH, I know how to do that. If I need to make something more acidic, I add acid to it. If I need to make it more basic, I add base to it. That's just standard neutralization reactions. All right, so for instance, talking about a particular acid that we've talked about before, we talked about in Chem 1, Chem 2, and even Intro that carboxylic acids, COOH, were weak acids. All right, technically, they have a Ka, and we're going to use pKa's a lot more often in this. Has a pKa of 4.76 to 3.75, depending on what it is. And that really is the range. Most carboxylic acids have a pKa of somewhere in that 4 to 5 range. And it really doesn't matter what else is attached here on carbon-wise. That's about where we're going to find our pKa's, right, in that 4 to 5 range. Now, that is weak acid range. Matter of fact, if I back up to that table, that's in perfectly right in the middle of weak acids. That's the definition of a weak acid. That's why we called it that back when we introduced an intro. And we're not changing anything. We're actually just pointing out that by changing what else is here, or what was here, we would adjust that pKa slightly. And we're going to see there's things we can do to make it adjust even more, but that's what we're talking about here is that bond. Now, specifically what's going on is we'd be ripping off that hydrogen and leaving the electrons behind, and it happens relatively easy in a water situation because that is a weak acid. So just adding acetic acid or formic acid to water, you're going to have a weak acid. All right, turns out there are other weak acids. I skipped a page. Alcohols, for instance, do actually have a pKa, 15.5. Now, if we backed up to that slide that talked about the strength of our acids, we'd see this is listed in the very weak acid. Matter of fact, water does have a pKa. It's 15.7. So these give up H's about the same amount as water does. And remember how water, if it was if water is pure, pH of 7, has 1 times 10 negative 7th molar concentration of H3O and OH. That's what we're talking about here. Very little bit is being produced. It's right on the edge of not even being considered an acid, but it is right there at that edge. So we can kind of call this a very weak acid without any too much difficulty, and we can safely kind of say that alcohols and all alcohols have a pKa right around 15. Now, we have another one on here that I want to talk about. Now, when you first think about this and you think about amines or nitrogen-containing compounds, you think base. And you would be right, because actually what happens on both of these, if we were to actually add ammonia to water, we would not expect this to act like an acid at all. The water would act like an acid, and we get OH minus and NH4 plus. That's what we would expect to happen, and that's what really would happen. But a very small percentage, let me get rid of all that ink I just wrote, is going to do something different. Instead of doing that with water and having the water like an acid, I want to know how likely it is to have the NH3 as an acid. That's what a Ka is for. It's telling us we're going to have the NH3 be the acid. So if the NH3 is an acid and it makes H3O out of the water, that means this loses an H, becomes NH2 minus. Well, I can write the equation. It is actually talking about how weak that actual bond is, but this pKa of 36 kind of tells us that it really doesn't happen. Remember how our rankings, once we got above 15, very weak acid, this isn't even what we consider a very weak acid. This is significantly weaker than a very weak acid. But we want to look at it in this way because it talks about the strength of that bond. In that NH bond, we know it's going to be very hard to break that off. That molecule is held together quite well. The only way I can get it to break is to put it in very extreme situations. And this pretty much, it's safe to say, it's not going to happen. Because if I were to put NH3 with water, we would expect the water to act like an acid. But we do have pKa's for that. And we have some other ones. we have some neat things that pop up. Turns out if I protonate the amines, I can significantly lower that pKa. What I mean by protonate it? Basically, let that NH3 act like the base and accept the proton. And once it's been protonated, once the amine's been protonated, suddenly this new species has a totally different pKa. And it turns out the pKa of a protonated amine is closer to 10. That puts it more acidic than the alcohols were. That's in that mildly weak acid range. And if I'm going to protonate this, I have to look at the fact that maybe I could protonate the alcohols and the carboxylic acids, and it turns out you can. A protonated alcohol actually is going to be have a pK in the negative range, closer to about 1 to 2. And a protonated carboxylic acid is going to have a pKa in the -6 range. Both of those would actually be considered strong acids. All right. Where does this help us? Turns out it's going to really affect that overall versatility and reactions. Alcohols, for instance, all of them have the ability to act like an acid because this bond can leave those electrons behind and have this H go off, and we can have this CH3O minus. And I can do the exact almost opposite thing. I'm going to have that lone pair of electrons on the alcohol accept a proton from water. Becomes a CH3OH2 positive, and then we just have water going on here. But I have a cation and I have an anion that both started with the exact same species. And these are both things that are reasonably possible because those pKa's tell us they are. I can actually have CH3 act like an acid and a base with reasonable performance. Now, I kind of can do that with carboxylic acids as well. Carboxylic acids can act like an acid. I mean, we expect that. pKa of this is around 4 to 5. So having to give up an H and become a negative species is definitely doable. If I put it with an OH, it's definitely going to happen. This would be an easy one to go forward. And even if I have it in solution and I throw in a pretty concentrated acid, I can view it's going to actually be able to put an H on there, and we can do the same type of thing. So we can have a carboxylic acid become an anion, and we can have a carboxylic acid become a cation. All right. Amines do the same thing. This first one is a little bit harder to do because OH, we're almost to the point of the pKa is too high for an amine because this is going to have a pKa around 40. It's almost too high for this to go forward very far. So that's why they're showing the arrow mostly favoring going backwards. But it can be doable. If I have a strong enough base, I can actually make this go forward and get that nitrogen with a negative charge on it. Now, having the nitrogen-containing compound behave like a base, far easier, because if I put that in with an acid, this is just a straight neutralization reaction, and this is exactly what would happen. Very easy to see that's actually happening because we do expect a nitrogen-containing compound to be a weak base. All right, so how can we make a call on if it's favorable or not, or more importantly, which one's the acid and the base when we're looking at the reactants? So I have two situations where we're looking at just the reactants. Now, both of these are ones we talked about in intro and even general chemistry, or general chemistry 1 intro, all of them. And we actually made a prediction, kinda, right off the bat. I mean, some of you are probably looking at this thinking, well, that's definitely acid because it's that strong acid. And that really is a good way to think about it. But the nice thing is even if it was two new species, and if you didn't know anything about them, if I give you this and you know the pKa, you know the one with the smallest pKa is the acid. The smallest pKa must be the acid, therefore in this case the water's the base. Yet over here, the smallest pKa is the water, therefore it's the acid. So if I know which one's the acid, I have it give up its hydrogen, and the other one becomes the conjugate acid. And over here, since the water is the acid, it's going to become OH minus, and it's going to give the other species, our base, the hydrogen. but we can always make that call based on just which one is a better acid by looking at whatever the pKa's are. All right, we can also decide which side of the reaction is favored by looking at the pKa of the acids on both sides. So I got the acids on either side here circled. And right below it, we figured out what the pKa's were. So all carboxylic acids have a pKa around 5. All ammonium complexes, ammonium ion complexes, nitrogen positive, have a pKa close to 10. All right, the stronger of these two is the smaller number. So this side would be the strong acid, this one would be the weak acid, and our arrow will always go away from the strong side. All right, on my second one, we know alcohols have a pKa around 15, and protonated amines have a pKa around 10. 10 is smaller than 15, strong acid, weak acid. Going to go away from the strong. All right, now, how do I actually guarantee I can predict those pKa values? Well, there is the possibility of just flat out memorizing every single pKa possible. Obviously, that's a little bit hard to do. So let's look at some trends we can relate to the periodic table. Now, if we're talking about the actual pKa's and how electronegativity talks about it, we're talking about the electronegative atom being directly attached to the hydrogen. Or the atom in question is the atom that's directly attached to the hydrogen is the electronegative atom we care about. And it turns out the more electronegative the atom is here, the stronger it is as an acid. HF is a stronger acid than H2O, which is stronger than NH3, which is stronger than CH4. And we just actually assign these values. So that was, 25, about 40. Haven't assigned this one yet. And HF is one of our weak acids. I think it's right around 5 on its pKa. All right, but we can make that call based totally on the electronegativity. Now, unfortunately, electronegativity is not the only way to do that. So we can't base all pKa's on electronegativity. But we can if we're going across on the row on the periodic table. Oh, I bumped it. Now, if you know the strength of the acids, you actually also know the strengths of its conjugate base, because a strong conjugate, or the stronger of the two weak acids, if we're looking at HF versus H2O, since HF is a stronger acid between these two, F minus is a stronger base than those two. Sorry, reverse that. Stronger acid has the weaker conjugate base. So this is a weaker base than this one. How about I label that? We're looking at these two, H2O versus HF. HF is a stronger acid than H2O, therefore the conjugates, this is a stronger base than this one. All right, now the thing about the stabilities is going to pay off later. It turns out if we have a strong acid, the base that's left over is actually more stable. So F minus is actually a more stable anion than OH is. All right, alcohols and amines do actually behave as weak acids, but they actually do some interesting things to actually explain what's going on here. So what we're talking about is the overall pKa's. Why are they that difference? And can we relate it to just the electronegativity? Well, yeah, we can. Oxygen, has electronegativity around 3. Nitrogen's electronegativity is around 2.5. The smaller the electronegativity, the weaker it is as an acid, and we see that in our pKa's. So that the fact that oxygen is more electronegative than nitrogen does perfectly fit in with our pKa's that we looked up before. Even when they're protonated, we hit the same trend. The more electronegative oxygen will be more acidic than the less electronegative nitrogen, even though they're both protonated. All right, now here's an interesting. This is dealing with just carbons and hydrogens. Now, we haven't talked about these at all yet, but a CH bond can be as weakly acidic as a pKa of 60. And that's how they mostly are. 60 is the standard, or where it starts. But if I actually make a double bond or a triple bond, that increased electron density of the double bond and triple bond makes that CH bond ever so slightly weaker. And if it's ever so slightly weaker, its pKa will be smaller because it's more acidic. And it turns out my CH of an alkene, or something with a double bond, is almost there with a nitrogen. Nitrogens are typically more acidic than a CH2CH2, but they're close. But a CH, if that carbon is triple bonded, is going to have a pKa around 25. So it turns out CHs have a pretty big diversity in their pKa's based on the carbon itself, what type of bond it has. Now, in the last chapter, we introduced the weird S character terminology, and we can actually say a carbon that has more S character is going to be more acidic than a carbon with less S character. Okay, size is the other factor that's going to fit in with strength of an acid. So we talked about electronegativity factoring into what makes a strong acid. Turns out size does as well. And what happens is the bigger an atom is, the farther apart this actual bond is, makes that bond weaker. So a bigger atom leads to a stronger acid. HI is a much stronger acid than HF. All right, now also with this strength of acids, that is, we're going to look at how electronegative species affect molecules when they're not directly connected to the hydrogen in question. So in this case, we've got a bunch of hydrogens, but the acidic hydrogen is the one that's part of our carboxylic acid. All right, and being a carboxylic acid, we'd have a pKa somewhere between 4 and 5, and this particular one has a pKa of 4.76. All we've done to this is on the carbon that's 2 carbons away from the OH, we've added halogens to it. Now, the halogens, being electronegative, are pulling electrons towards it. And that's what they're showing here. That withdrawing effect, pulling electrons away, makes that bond ever so slightly weaker, makes it more acidic. So having something electronegative attached to the molecule will make something more acidic. And the more electronegative, the bigger that effect is. Now, we also have to look at where it's at. So I went with a bigger molecule. This particular carboxylic acid has 5 carbons in it. Now, by itself, going to have a pKa of around 4 to 5. And I don't have that up here, but it's going to be about 4 to 5. But if I put a halogen way out to the end, the pKa is very similar to what we'd expect to see even without that. And that's going to happen whether it's bromine, chlorine, or fluorine. It's just far enough out that its withdrawing effect is minimized. But if I move it closer and closer and closer, we see the pKa's drop and drop and drop. That withdrawing effect is much more effective the closer the electronegative atom is. All right. Carboxylic acids and alcohols both have just OH bonds, but we actually put our alcohols pKa around 15, and we put our carboxylic acids with pKa closer to 5. Why is there that big of a difference, even though we're talking about just an OH bond? Well, we can see what's going on if we just look at what's made when the H comes away. So what their conjugate bases look like. And that conjugate base is just that same structure with the H removed, so that becomes a negative ion, and this becomes a negative ion. All right, so what's so unique about this guy that makes it more stable? Resonance is right. That lone pair that makes up that double bond moves down here, and the negative goes up, or vice versa. However you want to look at it, the double bond moves around. And having that double bond move back and forth, create these two structures, creates resonance contributors which create a resonance hybrid. And now, rather than have all that negative charge localized on one atom, you have that negative charge localized on two. That spreads that negative charge out, makes the anion more stable. And just by having that resonance provides it to happen more often. All right, so summary of our acid strength factors based on what the H is attached to. The H is attached to atoms on the periodic table, and you can look at where it's at on the periodic table to decide how acidic it is. As you get more, as you're going left to right across the periodic table, the factor that contributes most to the increasing of the acidity is the electronegativity. More electronegative, more acidic. If you're going up and down, it is actually size. The lower it goes down on there, the bigger the size is, and therefore the stronger it is as an acid. And hybridization affects it. The more S character, the stronger the acid. Less S character, the weaker the acid. And proximity of a withdrawing group or something that's electronegative. Now, electron withdrawing is probably a better way to think of it than just electronegativity, but they do mean the same thing. What I mean by electron withdrawing is something that's electronegative. And if you think about electronegativity and covalent bonds, almost every nonmetal has a electronegativity more than a carbon. So almost anything attached, like an oxygen or a nitrogen or a sulfur, is going to withdraw those electrons more and actually does make the acidity go up. So anything that's withdrawing will actually increase the acidity. And delocalized electrons or resonance structures help increase your acidity. Now, our most common one we're going to see is something like our carboxylic acids right off the bat, but there are alternatives that don't necessarily involve just COOH that will actually allow for resonance structures to stabilize. Okay, let's think about some math here. Now, what I have here is this Henderson-Hasselbalch equation. It is actually just a deviation of something we did back in intro and General Chemistry 1 and General Chemistry 2. All right, you might remember, hopefully, an equation that looks something like this for your Kas. That's not H2, that should be HA down there. So, all right, I'm just going to rewrite this and say it's Ka is equal to the H3O and times A minus over HA. And all this Henderson-Hasselbalch equation is, remember how H3O and pH, this is just the negative log of the H3O is the pH? Well, negative log of Ka is the pKa. And if I threw in the negative log here, we would have this equation. Now, you notice how this is positive log? Well, the only way to turn a positive log into a negative log or reverse the sign there is actually to invert this, which is why it's HA over A minus. So this Henderson-Hasselbalch equation is just a different way of writing this that shows us solving the pH directly from the pKa, which is kind of different than how I teach it in General Chemistry 1 and 2, but this is actually beneficial to what we're going to talk about now because we're not doing any math at all. I'm not going to need you to use a calculator on any test and use the log. I just need you to know a couple weird things about logs. Like, for instance, let's say these two values are the same thing. If this is log and if these are the same thing, that becomes 1. Well, what's the log of 1? The log of 1 is 0. So that term goes away. When these two are equal to one another, the pH and the pKa are the same thing, which is what we see here. When they're equal in amounts, the pH equals the pKa. All right, but I want to show you something else. Let's say we have a ratio of 10 HAs to 1 A minus, a 10 to 1 ratio. The log of 10 which is what this would be, is actually just 1. So what we see is something kind of neat. If we have 10 times the acidic form as the basic form, so like a 90 to 10 ratio, we actually are 1 full unit away from the pKa. And if we have a 100 to 1, 99 to 1 in this case, we have a pH difference of 2 to 1, or pH difference of 2. And the same thing happens if we go basic. If we have a 90 to 10% relationship between the base form and the acidic form, we are 1 whole unit above, and 99 to 1 is 2 units above. So the neat thing is we can make a lot of good calls about what the nature of our equilibrium is between the HA and the A minus, based on just how close the pH is to the pKa. Works on bases too. We'd be using pKb's, but same type of idea. You're just moving up and down below or above the pH of the pKa. Okay, now when we're talking about that acidic and basic form, we are talking about charges in some cases. Like for instance, when a carboxylic acid gives up its H, when a carboxylic acid goes from its acid form to base form, it gains a charge. And the charged form is that anion. Now, it's not always saying that the base form is charged, because my bottom one, I have a protonated amine, which is definitely charged because it's got that charge right there. But when this acts like an acid and it turns into NH2, there's no more charge. So we see charged forms on one side of all these equations always, because these equations always actually show the exchange of an H plus with something else. That H plus creates a charge because you're moving an atom with a charge. So you're always going to have a situation where a compound in your balanced equation has a charge. More than likely it's 2. And sometimes it's all 4 locations get charged. All right. Next little thing we're going to do is talk about some of the other terminology. Buffers was something we brought up. And in Chem 2, we did some calculations with buffers. Here we just want to talk about the fact that a buffer solution is made up of an acid and its conjugate base. But these two, the A's in this case, had to be the exact same thing. So you could have a relationship with acetic acid and acetate, but you had to have 2 compounds that were related on that A minus aspect, or the A part of it. All right, next little thing we're going to introduce is yet another type of acid. It's specifically the Lewis acid. Now down here at the bottom here, I have just the general acid equation. You got an acid neutralizing a pair of electrons, and that's the relationship. Well, what if this wasn't H plus? Every single time so far, we've been talking about bronze to lower, and even back on up to Arrhenius acids, you would have had an H plus. Well, I can get a very similar reaction to happen if I use this stuff called boron trihydride. So BH3 reacting with NH3, the same species, does actually give us this weird BH3 bonded to an NH3. But the reason it's similar is because the basic part of the NH3 would be neutralized. So this neutralization is happening because this is behaving like an acid. Lewis acids are simply acids that accept electrons. And what's happening here is that boron could have an octet around it, but it has an empty space. This would be a trigonal planar thing. That empty space is where that lone pair is going to attach. That empty space is what makes the BH3 an acid. Now, we have other types of Lewis acids we'll use in organic. Most of them are involving metal ions or boron. Boron and metal ions are the most common ones we see. But the metal ions all will have a very similar aspect. They will never have 4 things around them, but they will be something that more than likely can handle 4. And that empty spot is where we're going to create a temporary bond or a permanent bond. Well, in both these cases, that lone pair are being neutralized. So these are acid-base equations. It's just that our acid has no hydrogens, therefore it must be a Lewis acid. All right. When we use our terms, acid and base do get used, and they typically mean the exact same thing as they did in General Chemistry 1, 2, and even Intro. An acid is something that donates a proton, and a base is something that accepts the proton. When you have an acid that neutralizes a base but doesn't actually use it with protons, we actually will specifically call a Lewis acid. Now, something we're going to add to this term is nucleophile. Now, it almost has the exact same definition as a base. A base is just something that shares its electrons with a proton. A nucleophile shares its electrons. But we're going to say with an atom or other than a proton. So what I mean by that, if I have a nitrogen with a lone pair, if instead of an acid coming in here, let's say it's that boron coming in. Boron's not a proton. So even though it would be proper and could be said that that nitrogen is behaving like a base, we're going to call it a nucleophile in organic. Actually, it's going to be kind of more broad. Almost any time you see an atom with a lone pair on it, that atom with that lone pair can be considered a nucleophile, especially if you can do a reaction with that lone pair. If you can make that lone pair make a bond, then that species is definitely a nucleophile. Okay. Now, here's an interesting thing. So, our ions always have solubility in water. What do I mean by this? All right, so I want you to think of a very simple salad dressing, oil and vinegar salad dressing. This is a container in it. If we haven't mixed that up, any oil and vinegar salad dressing has a separation. Oil's on top, and your vinegar part or water is on the bottom. Now, the reason this is happening is because oils are typically really long carbon-containing compounds, and almost all of them in our food have maybe as many as 16 carbons, and then at the end we have a carboxylic acid. That's what most oils are. Anything longer than 16 carbons, they're going to be solids, and that's more like a fat. But oils are just really long chains of carbon, sometimes double bonds, sometimes more than one double bond, but really long carbons, and on the end of a COOH. And because of all these carbons, even though that can do hydrogen bonds and it's has that COOH, it's not going to be water soluble. This is going to be if we were to mix it with water, it stays solid. So all these oils stay up here. But if I have smaller ones, like vinegar, for instance, vinegar only has one carbon next to that. It has an increased solubility and it sits down in water. So that's why this natural product, oil and vinegar salad dressing, is something made out of organic material. It's a recipe. You grow everything that ends up in it. It is stuff that's going to be soluble in water and some stuff that's not. Well, we take advantage of these properties when we get into a lab to do some purifications. And it'd be really neat if I could somehow make these long carboxylic acid-based oils become water soluble, because I could separate them out of here. Because being that a layer like that, don't you see how we could maybe put a little valve on the bottom and drain out all the water and have a totally separate water from the oil? So we could figure out every single compound that's in the water. We could figure out every single compound from the oil. But how cool would it be is to drain out all this water and then add something to just the oil to get some of those carboxylic acids to turn into water-based substances? Well, we can. pH will change the solubility. And why is that? Well, let's think about this. I'm going to condense this. I'm going to have a single CH3 and then a CH2 in parentheses with an X. So it's a really long molecule. Well, if I treat that molecule with a strong enough base, I'm going to turn this into a carboxylic acid carboxylate, so the conjugate base of it. All right, well, so why did I do that? Well, here's something cool. While this, because it's really long chain, is not soluble in water, it would be in the oil layer. If I add this base to it, if I add enough of it to it, every bit of this would turn into an ion, and as an ion, it's now in the water layer. So here's something neat. Anytime I have a species that on one side is not charged and on the other side it's charged, I can throw the pH off and make it more or less water soluble. Most carboxylic acids, you add a strong enough base, will become soluble in water. We even take advantage of it with some medications. So you might have noticed a prescription drug with a really long name, and at the end it has the letters HCl in there. The reason they have that there is this thing here, whatever it is, probably has a nitrogen in it somewhere. Nitrogen-containing compounds, amines, typically aren't soluble in water when there's a lot of carbon. But that's pretty much not always the case. Why do you do HCl? Turns out most amines in their natural form stink. Either a fish smell or a vinegar smell. But amines typically have a smell that's unpleasant. Well, here's something neat we can do to almost any amine, though. If I actually can protonate that nitrogen, and what I'll do is I'll put this here and then make this whole thing become a positive ion. As a positive ion, and then the chlorine is a negative, we make it an amine salt. That amine salt will not have the bad smell. Matter of fact, it's actually incredibly water soluble. It's actually so beneficial that if you go to a place like a fish fish restaurant, Red Lobster, Long John Silver's, something they sell or have available is vinegar. And the whole purpose of having the vinegar is you have a piece of fish that smells too fishy. If you put vinegar on it, that will neutralize the smell. The smell is actually not nearly as bad if you add the acid to it. Most of them do a little bit fancier now. Lemon glaze or orange glaze fish. The lemon and the orange is acidic enough that it neutralizes the acidity of it. All right, that actually puts us up with our summary of our acids and bases. Now, I would encourage you to do the problems in the chapter, and even at the end of chapter 3, right at the end of it, there is a tutorial on acids and bases that deal a lot more with the classes we're going to deal with. So the actual individual pKa's of things like our alcohols and amines. I would encourage you to give a good look at that stuff and so you can get ready for this test.